In this video, we are going to cover an example problem where we have a 2 mole monatomic gas that has an initial temperature of 450 Kelvin, and the gas is then cooled under a constant pressure to 300 Kelvin. We want to know what the change in internal energy is, what the work done on the gas is, and what is the heat exchange with the environment. Alright, so a couple of key words here. The first being monatomic. So that's going to tell us some of our constants, and the other is constant pressure. Constant pressure means that we're doing an isobaric process, so we need to use these relationships here. So the first thing we're doing is finding the change in internal energy. So the change in internal energy is going to be found using the number of moles times the molar specific heat at constant volume times the change in temperature. So I plugged in the 2 moles. Molar specific heat at constant volume for a monatomic gas is 3/2 times the ideal gas constant. So I've done 3/2 times the ideal gas constant. And then I plugged in the change in temperature. Remember, change in temperature is always final minus initial. So I'm taking the 300 minus the 450, which is a negative 150 Kelvin. And then I am multiplying that all together in order to get that change in internal energy. In part B, we're asked what the work done on the gas is. Now, for isobaric, we have 2 options. We can use pressure and volume, or we can use temperatures. Since we're not given pressure or volume in the problem, but we are given temperature, our choice is made for us. So we need to use the fact that work is equal to the negative number of moles times the ideal gas constant times the change in temperature. So I plugged in number of moles, ideal gas constant, and the change in temperature. And that gives us the work done on the gas. In part C, we then want to find the heat. Heat is calculated by number of moles times molar specific heat at constant pressure times the change in temperature. So I plugged in number of moles, the molar specific heat at constant pressure, which is 5/2 for a monatomic gas, times the ideal gas constant, and then our change in temperature of a negative 150. And that allowed me to find the heat. Now, one thing you can do to check your answer is remember that you do have the first law of thermodynamics. So you can check and make sure that this statement is true by plugging this in here, and this in here. And both sides of the equal sign should be the same. And if it's not, you need to go back and check your work.